In this video, we are continuing our section on structural induction, and we will talk about recursive definitions for sets and structures. So here's the idea. We've seen that with recursively defined things, there are two steps. There's this basis step where you specify initial elements that are in the set or structure, and there's a recursive step, and that's where we give a rule to form subsequent elements using the ones that we already have. Okay, so let's do an example, which says, what set is defined by the following recursive definition? So the basis step says that 6 is an element of our set. The recursive step gives us a rule for producing new elements, and it says that if x and y are an S, then x plus y will also be an S. Okay, so what are the elements in S? Well, I know 6 is an S because that's the basis step. The recursive step says, well, to get new elements, take ones we already have and you can add them together. So if I take 6 and I add 6 to itself, 6 plus 6, well, that's 12, and I got a new element in the set. Now I can take any of these elements and add the same one to itself twice, or one of each and add it to itself twice to get new stuff. So if I were to do, 6 plus 12, I get a new element, which is 18. To get another one, I could take 6 plus 18, for example, which is 24. Or I could have taken 12 and added 12 to itself. That's another way, actually, to get 24. And if I keep going like this, I can see that, wait, if I take 24 and I add 6 to that, I'll get 30. And I can keep going to get new elements. And, just kind of observing these elements, it certainly looks like what we have here are the positive kind of integer multiples of 6. Positive integer multiples of 6. Multiples of 6. We have a strong suspicion that that is what our set is. And it turns out that is what it is. If we wanted to kind of more rigorously prove this, we could use something called structural induction. We could prove this with structural induction. And we'll show what that is in a future video coming up pretty soon. It's a type of induction that helps prove things about recursively defined sets. Okay. All right, so let's give another example of a recursively defined thing. So we have these recursively defined sets. We could also have recursively defined structures. And an example is rooted trees, which we've seen before. So let's give a quick recap. So here's an example of a tree. Remember, our definition is that a tree is a connected simple graph that contains no cycles. Simple means no loops, no multiple edges. It's connected, which means if I take any two vertices, there's a path connecting them. And no cycles, which means, there isn't something like an edge like this that lets me go kind of all the way around like that. No cycles in a tree. And we've seen that if we specify one vertex as the root and orient all the edges downward from that root, it becomes what's called a rooted tree. So for example, if I make D be the root, I'm going to draw a vertex at D, and I'll put that up top. And then there's 4 vertices connected to it, and I'll put them all underneath D. So D is connected to B, it's connected to C, to E, and to F. So now let me go ahead and draw those edges that D has to each of those vertices. And then B is also connected to A, so I will draw an edge from B down to A. So this makes it a rooted tree. So depending on who you ask about rooted trees, sometimes we draw the root at the top like this, sometimes we draw the root at the bottom. In our class, in the examples that we're going to be doing, I'm going to be drawing the root at the top and then drawing downwards. Okay, so I can also define rooted trees recursively. And here's a way I can do that. So I'm going to let T1 and T2 either be rooted trees or be the empty graph. So an empty graph is a graph with no vertices, no edges. So I'm going to define a new rooted tree using this rule, which I'm calling T1 star T2, by first creating a new root. So I'm first going to create a new root, and then I'm going to draw an edge from this new root down to the left, connecting with the root of T1, this first rooted tree. And I'll do that as long as T1 isn't an empty graph. Okay, and then I'm also going to draw an edge from that starting root down to the right, connecting with the root of T2, whatever this second rooted tree was, as long as T2 isn't the empty graph. Okay, so this sounds kind of technical. How does this work in practice? Let's do an example. Let's say that T1 and T2 are these two rooted trees. So if I want to make T1 star T2, this recursive rule says first create a new root. Create a new root. So I'm going to draw a new root. And then kind of underneath it to the left, I'm going to draw T1. So I'm going to copy T1 kind of down to the left. So T1 is this tree that has this kind of root and then 3 vertices kind of extending downwards from it. So step 2 says, well, draw an edge from this new root that I've drawn down to the left that connects with the root of T1. And I've now done that. Then draw T2 down to the right of this new vertex. So T2 goes down like this, and then down to the right, and then the right one goes down like that. And then I connect my new root to the root of T2. Okay, and there I have it. There I have my new rooted tree. So this is now T1 star T2, this new rooted tree. Okay, so, what can I do with these recursively defined rooted trees? I can use them to give a definition of a special rooted tree, which is what's called an extended binary rooted tree, or for short, I'll call this EBRT. So these are things that I can define with a basis step, which says I'm going to let the empty graph be an EBRT. That'll be a starting point. And then in my recursive step, it says, well, if I have B1 and B2 are both EBRTs, then B1 star B2 will be an EBRT. So we are going to create this set of rooted trees using this recursive definition. Okay, so what do these look like? What do these look like? Okay, so in step 0, I'm just going to write down, well, what are the EBRTs that I'm starting with? Well, so what are the ones I'm starting with? In the basis step, it just says the empty graph. The empty graph. That is, what I'm starting with. Okay, and then those are the only things I have in the basis step. Now I build new EBRTs using this recursive step. So far, the only thing I have to select from is the empty graph. So what I can do is I can take the empty graph, star it with the empty graph, and let's see what that's going to look like. So according to my rule, the rule says first, draw a new root. So I'm going to draw a new root. And then it says, connect it down to the left with this first graph, as long as that graph is not empty. But it was empty, which means I don't connect it down to the left. And then I connect this down to the right with this second graph, but as long as that one's not empty. But for me, that is empty, so there's nothing to connect it to. So unfortunately, I don't get to draw an edge down to the right either. Okay, so that's all this is. Empty graph star empty is just, well, I only end up doing step 1. I'm not able to do step 2 or 3 yet because these are both empty. Okay, so in step 1, I've now produced a new EBRT. It's just a single vertex by itself. Okay, so now things will get more interesting. So now I have these 2 EBRTs to work with. So in step 2, let's form some new ones. So I could, take my single vertex and star it with the empty graph. I could also switch the order. I could do the empty graph, star it with a single vertex. Or I could do single vertex, starred with single vertex. Let's draw all of these. So for each of these, I'll start off with step 1, which is create a new root. Create a new root for each of these. Okay. So for this first one, it says, well, this graph that's on the left, draw it down to the left. I'm going to draw that down to the left. because it's not empty, I can connect it with that new route that I drew. And then take this one to the right, draw it over here. But because there's empty, there's nothing to draw, and therefore nothing to connect with this new vertex, this new route. Okay, well, nonetheless, I got a new graph. Cool, I got a new EBRT. All right, for this next one, empty graph, I draw it to the left, so there's nothing to draw. Single vertex is over here, I draw that down to the right, and then I connect it with my new route. And I got a new EBRT. All right, for this last one, I draw this single vertex down to the left, connect that. This single vertex, I draw down to the right, and I connect that. Okay, awesome. So in step 2, I have produced now 3 new EBRTs. So I'm slowly building out more and more. So now I have 5 total EBRTs. So in my next step, I'm going to get a lot of these. So I will just draw a few couple, and then I'll just draw a few of these, and then I'll tell you how many there are going to be in total. But we'll explore that more in a later video. So as one example, I could take a single vertex, which I have already, and I could star it with this graph, that I just got here. I could do that. As another example, I could take the empty graph, and I could star it with this one. I could star it with this one. I'll put a parentheses around it. Or I could take this third, most complicated one that I have so far, and, I could star it with itself maybe. Okay, those are just 3 possibilities. There are many, many others. Let's just draw these. So for each of these, I would start off by drawing a new route. Draw a new route. And now I draw the single vertex down to the left. I draw this graph down to the right. Connect both of those to my new route. Connect both of those to the new route. Okay, cool. For this next one, empty graph down to the left, which means draw nothing. This graph down to the right. So I'll draw that graph down to the right, and then connect that with my new route. And I got it. For this one, let's draw both of these down to the left and to the right. So down to the left, I draw it. Down to the right, I also draw it. And then connect both of those to the new route. And I have it. So there are many, many more here in step 3. It turns out if I do all of these, there are actually going to be 21 EBRTs in this third step. And we'll actually show these in a later video. Shown in a later video. I'll just have a picture of all of them. Okay, so I want to end this video. Oh, sorry. One more thing I want to say about EBRTs, and then one final example. So in an EBRT, we might notice that any vertex either has 0, 1, or 2 children. Remember, children just meant like how many vertices are kind of underneath it as a rooted tree. So this vertex had 1 child, whereas this vertex had two children. Okay, so the fact that this number 2 is showing up is, kind of related to the fact that there's this binary term showing up in EBRTs. So EBRTs are data structures that aid in searching. And so one of the reasons why it's helpful to get an understanding of what they look like and to have these recursive definitions for how we build them. Okay, so one final example in this video of another type of rooted tree. This one is called a full binary rooted tree, or FBRT. So the key difference with these is now in the basis step, we don't allow empty graphs. There's got to be at least a single vertex. That's my starting point. And the recursive step is the same as before with EBRTs. Okay, so what do these FBRTs look like? For this one, I want to give you an opportunity to try making these, to try to do step 0, 1, and 2 for this. Pause the video for 3 minutes to try this. 4, 3, 2, 1, pause it and try it. All right, so hopefully you did that. Hopefully you paused it to try it. Let us talk about it now. So these FBRTs. So in step 0, I start with the ones that I'm given in the basis step, which is, well, it's just a single vertex by itself. Then in step 1, I take the ones I already have, and I can use this recursive step to build some new ones. I only have one FBRT so far, so I can only just do like a single vertex starred with a single vertex. So the rule says we'll create a new root and then draw each of these things. So draw this one down to the left, draw this one down to the right, and then connect those to the new root. Okay, and that's the only one that I can build so far. That's my step one. Now I have two FBRTs from which to build new ones. So in step two, there are three total possibilities. Either I could do my single vertex starred with this kind of one, this three vertex thing. I could do it like that. Or I could do it the other way around. That three vertex thing first, starred with the single. Or finally, I could do that three vertex thing starred with another three vertex thing. Okay, so, if I do these, for each of these, I start off by drawing my new root, new root, new root, and then I draw this thing to the left, this thing to the right. So draw a single vertex to the left, my three vertex to the right, connect them both with the new root. If I do that for the next one, I'll get a three vertex down to the left, single vertex down to the right, connect those both with the new root. And for the last one, I'd draw my three vertex to the left, my three vertex to the right. We connect those both with the new root. Okay, and these are just the first couple of FBRTs, just going down to step two. Okay, so over the next few videos in this section, we will talk about some properties of these binary rooted trees, and eventually start to prove some results about these using structural induction.